Welcome to Acme Electric Transformer Seminar. In this session, we will be discussing K-factor transformers, harmonic mitigating transformers, and I-trap neutral current reducer. Harmonics are a sinusoidal waveform with a frequency that is an integral multiple of the fundamental frequency. For instance, if 60 Hz is the fundamental frequency, then 120 Hz would be the second harmonic, 180 Hz would be the third harmonic, and so forth. Both the fundamental 60 Hz and the fifth harmonic 300 Hz are purely sinusoidal. All harmonic frequencies are sinusoidal when viewed individually. In the next slide, we will see that they can appear as complex or distorted waves when viewed simultaneously. Here, we see a typical waveform of fundamental and fifth harmonic together. Notice the distorted or non-linear shape. Harmonics primarily originate in electronic power converters. These can be found in switch mode power supplies, electronic ballasts, variable frequency drives, oven and furnace controls, and rectifier circuits. Harmonics originate anytime current is being drawn in short, rapid pulses rather than in a smooth, continuous manner. Some of the problems that can be created by harmonic currents are overheated neutrals, overheated transformers, malfunctioning of equipment due to excessive voltage distortion, burned out motors, tripped circuit breakers, and blown fuses. It should be noted that a major side effect of harmonics is extra heating in all system components. TRIPLEN harmonics include the third harmonic and all the odd multiples of the third. For example, the 3rd, 9th, 15th, 21st, 27th, 33rd, and so forth. It should be noted that TRIPLEN harmonics tend to add up in the three-phase neutral conductor. "60 Hz or fundamental currents tend to cancel in the three-phase neutral because of the 120-degree phase shift between adjacent phases. TRIPLEN harmonics add up in the three-phase neutral because they are in phase with each other. The effects of harmonics on transformers include increased temperature rise, increased neutral current flow, increased core losses, increased sound level, and decreased efficiency. Stray losses in the conductors get multiplied by the K-factor of the load to increase winding rise. TRIPLEN harmonic currents add up in the three-phase neutral. Harmonic voltages tend to increase losses in the iron core. The K-factor is a mathematical formula for calculating the heating effects of harmonics. It is a measure of a transformer's ability to withstand the heating effects of non-sinusoidal harmonic currents created by much of today's electronic equipment. The stray losses of the transformer are multiplied by the K-factor of the load, resulting in increased heating of the unit. Next, we will discuss transformer conductor losses. Transformer conductor losses are composed of AC and DC losses. AC losses equal stray losses. DC losses equal I squared R. Total conductor losses equal AC plus DC losses. I squared R losses can be easily determined from current and resistance. Stray losses are more difficult. Transformer total losses can be measured by putting a wattmeter in the primary supply circuit. The I squared R losses can be subtracted from this total, and the remainder would be the stray losses. In this example, we see a standard distribution 75 kVA transformer has 2,995 watts of total conductor losses at K1, assuming a linear load. However, if the load would not be linear, for example at K20, the new losses would be 5,560 watts. This would increase the transformer temperature rise from 150 degrees Celsius to 244 degrees, resulting in overheating, shortened transformer lifespan, and possible cause for failure. There are three solutions to harmonic problems: K-rated transformers, harmonic mitigating transformers, and I-trap neutral current reducer. First, we will discuss K-rated transformers. K-rated or nonlinear transformers do not eliminate harmonics. They are only designed to tolerate the heating effects of harmonics created by much of today's electronic equipment. K-rated transformers are traditional delta-Y transformers. They are designed with lower flux densities and no load losses, as well as lower I²R losses, resulting in a larger and heavier unit. They do not eliminate or cancel harmonics. K-factor features include being available in K-factors of 4, 13, and 20. They are available with aluminum or copper windings. They have temperature rises of 150, 115, or 80, and they are UL listed and CSA certified. As of January 1st, 2016, K-rated transformers must comply to the efficiency standards, DOE 2016, of the National Energy Bill. They are only required to comply with a connected load condition of K1, no harmonics. Next, we will discuss harmonic mitigating transformers. They consist of a delta primary and a ZIG-ZAG secondary. The ZIG-ZAG secondary causes a phase shift in the TRIPLEN harmonics, which results in a canceling effect. This prevents the TRIPLEN harmonic losses from being coupled back into the primary and results in cooler operation and increased energy efficiency. Let's discuss what a ZIG-ZAG winding is. The secondary winding on each magnetic leg of the core is wound in two separate sections. These sections are then transposed between different legs of the core to create the ZIG-ZAG secondary. Each 120-volt output of the transformer consists of two sections from different magnetic legs, resulting in a magnetic phase shift. Here we see a diagram that shows the delta primary and the ZIG-ZAG secondary. There are several benefits to harmonic mitigating transformers. Unlike K-rated transformers, harmonic mitigating transformers actually treat the TRIPLEN harmonics in the ZIG-ZAG secondary winding. They reduce supply voltage flat topping caused by nonlinear loads. They improve overall power factor of supply systems. They are suitable for K-factor loads. And they provide improved energy efficiency, which meets the DOE 2016 at K1 load. Mitigating transformer features include copper foil conductor to minimize skin effect of harmonic currents, 2 taps at 2.5% above and below nominal, 220 degrees Celsius insulation system with 150 degrees Celsius rise, UL listed and CSA certified, and 0 degree angular displacement between primary and secondary windings. Harmonic mitigating transformers don't treat harmonics or neutral current until they reach the transformer windings. Harmonic mitigating transformers has 200% neutral bar. Neutral conductor from the transformer to load panel should be sized at 200%. Acme transformers have definitive advantages. Acme utilizes special winding techniques and foil conductors in both its K-factor and harmonic mitigating transformers to minimize the heating effects of harmonic currents. The use of foil conductor increases the dielectric strength of the insulation because one layer is only one turn. Foil also eliminates the effects of axial forces, which can result in failure of wire-wound transformers. Next, we'll discuss skin effect. Skin effect is directly proportional to the height or thickness of the conductor. Some manufacturers use parallel strands of thinner wire to reduce skin effect, but Acme uses foil conductors to get maximum reduction of skin effect. Applications that use harmonic mitigating transformers are hospitals and healthcare facilities, commercial and educational facilities, airport facilities, telecom facilities, broadcasting facilities, internet service providers, and data centers. Next, we'll discuss an I-trap neutral current reducer. The technical description of an I-trap neutral current reducer is that it is low impedance, zero sequence, and is an auto zigzag transformer. Some applications of an I-trap neutral current reducer are: it is used to reduce excessive current flow in the neutral of a three-phase 208 delta 120 volt system. It is available in amp ratings of 100, 150, 300, and 450. It includes a front-mounted amp meter for monitoring neutral current. Target areas include data processing centers, hospitals, radio and TV stations, large computer labs, and so forth. Any area having numerous electronic 120 volt loads powered from a 208 delta 120 system. How does the I-trap work? The third harmonic currents are in phase in the three-phase neutral. The low impedance and auto zigzag characteristics of the I-trap target the third harmonic currents, causing them to become out of phase in the three-phase neutral, resulting in a canceling effect. Reductions of 50% to 90% are typical. In many applications, the Acme I-trap provides an easier and more affordable solution than replacing existing neutral conductors. I-trap helps reduce unbalance in the phases, which helps reduce neutral current, as we see here in this slide. The I-trap is not a harmonic filter, but it does tend to reduce total harmonic distortion in the phases. It also slightly reduces the K factor of the system, which allows the supply transformer to operate a little cooler, resulting in longer life. If this transformer is ever replaced, we recommend that it be replaced with a K factor unit. Here we see that the total neutral current of 84.8 is greater than the highest phase current of 63.2. Notice that the total neutral current has been reduced by almost 90%, 84.8 to 8.1 amps. If you have questions about any of the transformers discussed in today's session, call us at 1-800-334-5214, or you can email our tech group at pdtechsupport@hubbleacme.com.